Yeah, once again, thanks for having me here today. That's my pleasure to share my research with you. And most of things I'm doing are method development, so my motivation will be quite short. I'm essentially trying to develop a method which will be capable of simulating electron transfer, proton transfer, and proton-coupled electron transfer. So one thing to simulate them all. On top of that, I would like to do something close to reality. And in reality, we have these transfer processes happening either at interfaces or in some very large biosystems. So we need to account for interactions with nearby environments. So I would like to go for something like 5 to 10,000 atoms. On top of that, I'm not really a QMMM or MM guy. I would like to treat all the electrons in my system quantum mechanically. And one more requirement is I would like to also treat a few selected protons, which might undergo this transfer reaction also quantum mechanically. And if you think that I wish too much and I'm just crazy, I will spend the rest of my talk convincing you otherwise. So my belief is that it's possible to do that if we combine, if we create a combined theory from these three blocks. So I essentially like to use subsystem density functional theory to treat large molecular systems. I would like to use a technique of constructing quasi-diabatic states or localized states to compute coupling elements between such states. And then I would like to also use this NEO framework or nuclear electronic orbital approach to treat quantum effects of few selected nuclei or protons in my case. So let me just walk you through all these three components one by one and discuss also how these things interact with each other, starting from subsystem density functional theory. So the idea here is that in subsystem density functional theory, we split our total molecular system into subsystems based on electronic density. So I'm simply writing this total electronic density as a sum of subsystem densities. Then every subsystem density is defined by corresponding molecular orbitals, which are centered at this specific subsystem. And these guys, in turn, are generated from atomic orbitals, which again centered at only this specific subsystem. So different subsystems don't share atomic orbitals, and molecular orbitals of different subsystems are not necessarily orthogonal. If now I plug this expansion into the normal energy expression from DFT, I will have more or less familiar terms, and here I essentially use colors to tell you that these black terms are not problematic. We can compute them all. Then blue terms is where we need to use some approximations, which are available, and then there are problems. So here, for example, you see that I'm writing a sum of kinetic energies of different subsystems, all being defined, all being computed from corresponding molecular orbitals. Then I have electron-nuclear interaction and Coulomb interaction. Everything here is fine. I can also split these terms, or I can keep them as whole. It doesn't really matter. I can compute all components. I have everything. This is essentially exchange correlation energy of my entire system. So I split it to subsystem contributions, and because this property is not additive, I need this non-additive correction. Again, everything can be computed. I assume that Kohn-Sham approximations, Kohn-Sham functionals can be applied here. And as long as I don't have orbitals in them, as long as I'm not using hybrid functionals, all these components can be computed because I can always get the density of a single subsystem. And if I sum them up, I will get the density of the total one, and then difference between functionals will always give me non-additive correction. But this guy depends on orbitals, and I no longer have one big set of orbitals spanning the entire molecular system and being orthogonal. So I don't know how to compute this guy. There are a few ways how to approximate this using explicit functionals of the density, but approximations are not as good as what we have for exchange correlation functionals. So a lot of work is still going on here. And so far, that's a problem, and I will return to this in a few slides and explain it in more detail. For now, let's just think what to do next. And the next step is usually minimization of the energy expression with respect to molecular orbitals. But in this subsystem framework, I'm not minimizing with respect to everything. I'm just picking one specific subsystem. I call it active. I assign it some index, let's say index K. And then I'm saying I'm minimizing the energy expression only with respect to molecular orbitals which belong to this subsystem K, to my active subsystem. What I have is this set of equations which look somewhat familiar. For example, this part is pretty much taken from Conchem DFT, and effective potential is also same as in Conchem DFT, but defined for subsystem K, and depending on the density of this active subsystem. And then there is a new beast here, which is embedding potential, and its goal is to account for interactions between our active subsystem with all the rest subsystems we are not optimizing yet, which are sort of frozen. So just to give you an idea what's happening in practice, if equations are not clear enough, let's say I have a cluster, a water cluster. Then what first thing I do, I split it to subsystems, and in this particular case, each water molecule can be a separate subsystem. Then I extract this first water molecule and compute it separately in vacuum, so it doesn't interact with anything, and I'm solving just normal DFT equations. Then I do so with the second, third, fourth, fifth, and by the end of the cycle, I have isolated densities of each molecule, so they don't feel interactions. Then I combine everything all together, and now I'm optimizing or relaxing the density of the first water molecule, keeping everything else fixed or frozen, and all interactions are here in the embedding potential. And by doing so, I can relax the first water molecule, and then I can go in a cycle and relax all of them. So if I, let's say, interested in a specific part of my system, I relax only this part, and everything else is, well, it can be described on a, as unrelaxed or partially relaxed. Then it's going to be frozen density embedding. If I continue such cycles again and again until my energy fully converges, then it's going to be subsystem density functional theory. If here in the embedding potential, which depends on this problematic non-additive kinetic energy, if I approximate this exactly, then by solving the entire problem iteratively and converging it fully, I should get DFT solution for my entire system. However, that's not the case, and we can regard this entire approach as an approximation to DFT. So I guess advantage of doing that is clear, because at each point of time, I'm solving DFT-like problem, which scales as n cube, but n here is a number of atomic orbitals of a single subsystem. So we reduce dimensionality quite a lot. And then the entire scaling is almost linear with the number of subsystems. In other words, we reduce dimensionality and we can compute much, much larger molecular systems than accessible with DFT. In this example from 13 years ago, for example, people created a model for the phenamethyl-olsen protein complex, which contained roughly 7,000 atoms. So that was doable back then, and these days we can go for even larger systems. As I said, there are no perfect or very accurate approximations for this non-additive kinetic energy. That's not necessarily a problem if subsystems are, let's say, separated far away from each other in space, or they're just weakly interacting. Then this contribution is just nearly zero. However, it becomes a problem if we have strong interactions, then contribution is growing. And the worst case scenario, if we have one big molecule and we try to cut it to pieces. So we can't cut through covalent bonds. This entire approximation will just break. Unless, of course, we do some advanced tricks, but that's a story for another time. So you might wonder what is possible to compute with such a method if I can't cut through covalent bonds, and this might sound as a big limitation for the entire approach. One example could be organic crystals, where we have just a large number of organic molecules arranged in space, no covalent bonds in between. Or maybe we're interested in biosystems, for example, in photosystem 2, where we will have a large number of different cofactors which are not covalent to bond. Of course, there is a protein around, and we need to describe it as well, but we can always take pieces of this protein, saturate valences, and by placing these pieces around, we can simulate a nearby environment. For example, if we're interested only in a central pair of chlorophylls, it will be enough to simulate like a couple of angstrom around it, maybe 4 to 5 angstrom. We will still be able to go for thousands of atoms in this way. And of course, molecules in solutions or ions in gas matrices. So all these examples exist, and you can see if you check the papers that results are also not too bad. So they are often qualitatively correct. So that's about subsystem density functional theory. Now we go into how to construct actually localized states and how to simulate transfer reactions. I'm still using the same framework of subsystem density functional theory, but now I'm considering this charge transfer reaction where I have a donor of charge and I have an acceptor, and here you see that reaction goes and the charge just flips from one molecule to the other. Now I can try to use subsystem density functional theory, and by doing so, I'm computing D plus in the environment of A. I compute A in the environment of D plus. Essentially, I'm free to place the charge whenever I wish because subsystems don't share atomic orbitals. The charge will stay on the molecule where I put it. It will not go away. And by doing so, I can compute a charged molecule in the environment of another one. I will account for all interactions via embedding potentials, and I can do so for left-hand side and the right-hand side. In the end, I will have molecular orbitals of both sides. So I can construct one big wave function for the left-hand side, which could be a Slater determinant, for example, composed of these molecular orbitals, and the same for the right-hand side of this reaction. And then this is an oversimplified consideration. Reality is more difficult, but the idea is that we can compute coupling terms. And this gives us an access to electronic couplings, which are connected to reaction rate constants. And then that's the way how people try to simulate electron transfer reactions and in very large biochemical systems. So this was done quite some time ago by Michele Pavanello and Johannes Neugebauer. And I had my share of work trying to extend this approach and make it applicable to even larger systems. For example, I made it applicable to computing electronic densities, charge densities, and spin densities, such a way that we can study how density redistribute between several molecules while being surrounded by huge protein environments. And then we can essentially get results and compare them versus experimental results done for these huge biosystems. I also was doing similar computations assessing various models proposed by experimentalists, and some time trying to extend this methodologically such a way that we can couple not just two states, but a variety of states. And then we can maybe study charge distribution in such stacked systems being charged. And of course, it's extendable. So as soon as we have density, we can compute whatever we wish. And in this case, it was a benchmark for isotropic hyperfine coupling constants. So it works. It's qualitatively correct. So essentially, I told you how to compute large systems and how to do computations of coupling terms, which are important for transfer reactions. And now what about NEO? So the idea of NEO is very simplistic. We just need to take a few protons, which, as we assume, will undergo a proton transfer reaction, and then we treat them as if they are electrons, essentially. We will create another set of atomic orbitals. We will center these atomic orbitals at positions of these quantum protons. We will consider Hamiltonian, which now will contain additional terms like kinetic energy of quantum protons and all sorts of interactions, proton classical nuclei, proton-proton, proton-electron, and we can derive whatever theory you wish, whether it's neo-Hartree-Fock, neo-DFT, neo-couple clusters, whatever you can imagine. In the context of neo-DFT, we have the energy being not just a function of electronic density, but a functional of both electronic and protonic densities. For electronic terms, expression will be similar as we have in quantum density functional theory, just kinetic energy, electron-nuclear interaction, Coulomb, and exchange correlation. Since protons are treated on the very same level with electrons, we will have exactly the same terms, but now defined for quantum protons and depending on densities of these protons. And then, of course, we have interactions between quantum protons and electrons. Here you see just Coulomb interaction between electrons and protons. And then that's a new thing, that's electron-proton correlation. And for that, we need an additional functional, but such functionals were proposed recently, they work, so it's not a big problem. It's only a matter of time when people come up with even better functionals and the accuracy is improved. But it already works rather nicely. Then, of course, we need to minimize the energy as we do in DFT, and if we do so, we will get this expression, which we already know from quantum density functional theory for electrons, and we will have an additional set of equations, very similar equations, but for quantum protons. They're coupled because of these coupling terms here. So we need to solve both of them at the same time and solve consistently. And yeah, several algorithms were proposed, whether we solve one and then go and solve another and do it iteratively, or whether it's a simultaneous DIS procedure. There are ways to do so. And then what you can get is this funny picture where you can maybe plot protonic densities of your quantum protons, which I personally find quite fascinating to see, and you see how much they are localized. So, given that we create such a framework where we have subsystem density functional theory and we can treat protons, we can then try and construct simultaneously proton and electron localized states, such a way that I can compute this state and this state, for example, which will be initial and final states of simultaneous proton-coupled electron transfer reaction. Or we can also construct these intermediate states, which will correspond to what we have when this reaction goes stepwise. And if we do so, then we can, in principle, compute couplings between pairs of such states. And these couplings will give us some idea about the reaction mechanism, hopefully, if the accuracy allows so. So that's essentially the idea. And as you can imagine, it's a very long road to the final goal. So I decided to use Serenity package for that, which already contained all the embedding methods like subsystem density functional theory. And then I needed to go and implement all these localization procedures, which we called FD diap, quasi-diabetization within the frozen density embedding. And more recent work is also introducing all these NEO features like restricted NEO Hartree-Fock, restricted NEO DFT, then introducing slated determinants for quantum protons and so on and so forth. So it's work in progress. And hopefully this year I can also release NEO subsystem density functional theory, or at least NEO frozen density embedding, where I maybe not optimize everything fully, but at least partially. So that's pretty much the overview of all the work which was done for the last years. As you can see, I am also not giving up on non-additive kinetic energy functionals, and I'm trying to improve these functionals for subsystem density functional theory. And of course, all the rest is about localization and NEO, so that eventually I have this framework and I can simulate various transfer processes. So with this, I would like to thank a few people. First of all, Beate Paulus for hosting me at the FU Berlin and allowing me essentially to do my independent work while being funded by DFG Eigene Stelle. Team of Serenity developers for reviewing my code and telling me what I did wrong there. And of course, everyone who is involved into this project, which are mostly my master and bachelor students. And of course, all of you for your kind attention. Thank you.